Hello everyone, we are from the Alternative Fields Laboratory of McGill University in Canada. Our presentation is about flame propagation, and more specifically, we would like to present non-volatile fields and in the field lean condition. I would like to start with how the literature normally address the heat propagation of non-volatile fields. We basically can use the same heat propagation equation that we normally use for the gas flame combustion, with the only exception that this reaction term need to be modeled differently by considering the kinetic and diffusion combustion region of non-volatile fields. By doing so, we will see a temperature separation between the burning particle and the surrounding gas, and we'll get this 1D temperature profile. It is based on the logic that if we project it in the three-dimensional space, we will only see the temperature non-uniformity in the propagation direction of x. In other words, in the lateral direction of y, we will see uniform temperature. But this temperature profile comes with a very huge hidden assumption. It is only true if we have a case where the heat diffusion rate is a lot faster compared to the heat release rate of the burning particle. And this is normally how the pre-existing literature models the metal combustion for non-volatile fields. And now the question is, what if the opposite scenario is also true when we have a heat diffusion rate a lot slower compared to the heat release rate from the burning particles? To answer this question, we have created a simple simulation by only considering two burning particles. And this simulation obviously tells us that now the temperature non-uniformity is not just in the x direction of propagation, but also in the lateral direction of y. And we can see this temperature non-uniformity doesn't disappear very soon. It's pretty obvious even though the particle is already finished burning. And in this case, we can expect the temperature build out a lot slower compared to the previous case, because we can see the heat is locked around this burning particle with this temperature microgradient at the discrete location of the particle. And therefore, in our publication, we call this discrete flame. Interestingly, this discrete flame actually is a common behavior for the field-lean mixture for non-volatile fields. Because if we have a field-lean mixture where the particle separation is quite significant, we know that this burning particle only collects the oxygen from its surrounding at a small radius. And if we consider Lewis number equal to 1, this heat diffusion needs to go through a much larger length scale compared to this small radius for the oxygen collection. And therefore, this case is true now. If we have a field-lean mixture, the heat diffusion rate will be a lot slower compared to the heat release rate from the particle. And why do we care about discrete flame? It's because if we consider this temperature microgradient, we can actually see several features that we normally do not see in the conventional gaseous flame combustion. So now I show you the same simulation from the previous slide, and we are tracking the temperature of this unburned particle. And we repeated the simulation with another combustion time, which is 2 times slower. And we see from this simulation at the beginning, it seems that the temperature profile is quite different for both cases. But after a certain period, because the particle combustion time is so much shorter compared to the heat diffusion time, so the particle combustion time doesn't matter anymore. We see quite similar temperature profile and also similar temperature value of this unburned particle for both cases. So we can expect this unburned particle ignite almost the same time. Therefore, the flame speed is independent of the particle combustion time of the burning particle. We know that this unburned particle will be ignited at a certain time step when it reaches to the initial temperature represented by this green plane. And now we are interested to know what if we move the location of this unburned particle. And because of this temperature non-uniformity, now this particle is able to reach to the initial temperature faster and can be ignited at an earlier time step, even though they are in the same y lateral distance. So the consequence is that if we have many particles at the random location in this 3D space, we can just see them ignited like randomly without any clear sequence. And this is definitely not like a layer by layer emission that we normally see in a gaseous flame combustion. And at certain time step, we can even see the propagation is going sideways in the lateral direction. So the consequences from this temperature non-uniformity is that we do not see a clear flame front separating the burnt particle and the unburned particle like what we normally see in a gaseous flame combustion. And now I would like to discuss the discrete flame propagation limit. We can first define a simple thermodynamic limit, which is based on the fact that we need the field concentration that can generate the flame temperature higher than the initial temperature to make the flame propagation possible. And Francois Tang has studied this flame propagation limit further by having a rectangular grid where all the particles are regularly spaced between each other. So the simulation result from this paper are showing us that if we have a heat diffusion rate a lot faster than the heat release rate, the propagation limit actually is approaching the thermodynamic limit, which means it is basically limited by the initial temperature. And now if we have another extreme case where the heat diffusion rate is a lot slower, now we see the propagation limit is about 2 times higher than the thermodynamic limit. And that is because of this temperature microgradient again. Because most of the heat is locked around this burning particle, so not all the heat released from a particle is participating in the flame propagation. So the consequence will be we will need a much higher field concentration to generate the flame temperature about 2 times higher than the initial temperature to make the flame propagation possible. And now interestingly, if we randomize the position of this particle instead of regularly space them, we can see some interesting features here. First, we see that instead of just having a single defined limit like the thermodynamic limit, now because of a random position in different run, we see different probability of propagation at different field concentration. And secondly, we can also see that because of a randomization, some of the particle can be closer to this temperature microgradient, so fluctuation of the particle can actually help the flame propagation easier. We can see, let's say like 1.5 for the concentration here. It's not possible to propagate in a regularly spaced model, but it is possible with some probability of propagation here if we randomize the position of the particle. And lastly, we can see that the propagation probability is also a function of the width domain of the system. And the probability curve, the meaning is actually, if let's say we take 0.6 for the propagation probability here, it means that if we run the simulation n number of times at the same field concentration, 60% of the time, the flame can propagate from one end to the other end. And I would like to emphasize that the other 40% doesn't mean there's always no propagation. It may still have the propagation, but the flame cannot reach until the end. But it can propagate and quench at the different location with different propagation length. So this simulation shows us another unique behavior is that the propagation of discrete flame is completely statistical in nature because it really depends on the spatial arrangement of the particle, which is randomized at different run. So how the unbound particle interact with a temperature microgradient also can be very different in different run, even though at the same field concentration. We have seen very interesting behavior for the discrete flame from the simulation model, so the goal is also to validate it in the experiment. The experiment will need to observe the particle interaction in a slow propagating flame, and the particles also need to be distributed uniformly, just like what we see in the model just now. So the only way is to do it in a microgravity platform because we want to eliminate the effects of natural convection and also particle sedimentation. So as of now, our group has launched 3 sounding rocket missions, and here you can see our combustion apparatus and with a combustion tube. We use iron as a non-volatile fuel here, and the particle will be distributed from the closed end of the tube toward the open end of the tube, and then there's an ignition wire here to ignite the particle, and our flame can be observed from by the high-speed camera and the 3D camera system here for the flame structure. We also have an overview camera to observe the flame speed and flame propagation length. The first sounding rocket campaigns was done by one of my colleagues, Palecka, in 2017. Here we can see there are 2 different oxidizing environments, one with 20%, the other one with 40% of oxygen. So obviously the particle combustion time will be significantly different for 2 cases. But the experimental results show us that the flame speed do not significantly different from each other, even though they have a very different particle combustion time. So these campaigns our groups concluded that the conventional model that suggests that the flame speed is depending on the particle combustion time is not valid if we have a heat diffusion rate is a lot slower than the heat release rate from the particle. We also have a parabolic flight campaign in 2021, and here we can see if we have a high concentration of discrete flame, somewhat there's a clear flame structure, and if we project it in a 3-dimensional space, we can also see there's a dome-shaped structure, and this is normally what we see for the gaseous combustion in a tube. And now if we go to the low concentration where the discrete effect is more significant, we now see random emission of a particle like everywhere without a clear flame structure, and we can also see the flame doesn't always go forwards, and this is definitely not a layer by layer emission with a clear frontal structure that we normally see in a gas flame combustion. Our second and our third sounding rocket campaigns, we focus more on the propagation behavior of discrete flame, and here we measure the propagation length of the flame in our combustion tube. If we have a high concentration for the fuel, we expect the flame can always propagate until the maximum possible endpoint as shown in our experiment here. But I think we are more interested in the low concentration where the discrete flame behavior is more obvious. So here you can see different runs, we have a very similar fuel concentration. So intuitively, we will expect the propagation behavior is quite similar. But the experiment result clearly shows us that their propagation length is quite different, and some of the run can even propagate until the maximum possible endpoint. And here from the experiment, we can clearly see that the statistical nature of the discrete flame, because even though the fuel concentration is quite similar, the propagation behavior in terms of the propagation length can be very different. This statistical nature of discrete flame is the key message of our presentation. We know that from the conventional theory, normally there's a single well-defined limit for the propagation, above which the flame can always propagate. But for the present study, we show that even though at the same field concentration, sometimes the flame may propagate, sometimes the flame may not propagate, and they terminate at a different propagation length. We also see from a simulation that the probability of the propagation is a strong function of the width domain of the system. So to close this presentation, my open question is that if we can ever have a very large, infinitely large width domain, can we ever converge this probability curve in a way that we can still define a single well-defined propagation limit for the discrete flame, even though with a random spatial arrangement of the particles? And what will be the value for this propagation limit? And finally, I would like to acknowledge the financial support, especially from the European Space Agency and the Canadian Space Agency. And if you have any question, please do not hesitate to reach out to us at this email. Thank you so much for your attentive listening.